Welcome back, everyone, to Cosmic Queries. Today we're diving into a topic that, believe it or not, still sparks some pretty heated debates. It's something we probably learned in kindergarten, but what if there's more to it? What is the real form of the Earth?
That's right, Don. It sounds like a settled question, doesn't it? Globe, sphere, done. But scratch the surface, and you find a fascinating rabbit hole of history, science, and a good dose of skepticism. We're talking about the shape of our home planet and how we actually know what it is.
Exactly. We all grew up with pictures of a blue marble from space. But then you hear people, and sometimes very passionately, questioning that. They say, look around you, it's flat. And you have to admit, standing on a beach, the horizon does look pretty level.
It absolutely does, and that's the core of the human experience that fuels some of these alternative ideas. Our immediate perception. But then, how do we reconcile that with, say, planes flying around the world, or ships disappearing hull first over the horizon?
Those are the classic arguments, aren't they? The ship example is compelling. You see the mast last, it implies a curve, but some might say it's just a trick of perspective or atmospheric conditions. It gets wild when you dig into it.
It does get wild. Let's start with the universally accepted scientific model. The Earth is an oblate spheroid. Not a perfect sphere, but slightly flattened at the poles and bulging at the equator due to its rotation. Think of it like a squashed ball.
Oblate spheroid. Even that sounds more complex than just a ball. So, it's not perfectly round, but close. And how long have we known this, scientifically speaking? Because I recall stories about ancient Greeks figuring this out.
Oh, absolutely. The idea of a spherical Earth isn't new at all. Eratosthenes, a Greek mathematician, famously calculated the Earth's circumference with remarkable accuracy around 240 BC. He did it using simple geometry and observing shadows in two different cities at the same time.
That's incredible, isn't it? Two cities, shadows, and boom, you've got the circumference of the planet. No satellites, no rocket science, just pure observation and math. It really puts things into perspective about human ingenuity.
It really does, and his method implicitly relies on the Earth being curved. If the Earth were flat, the sun's rays would hit both locations at the same angle, and there'd be no difference in shadow length to measure. So, for thousands of years, educated people have known it's a globe.
But then, why the resurgence of flat Earth theories? It's not just a fringe thing anymore, it's gained a noticeable following online. What's driving that, do you think? Is it just distrust in authority?
That's a huge part of it, Don. In an age of information overload and often misinformation, people are naturally skeptical. They're encouraged to do their own research, which can be empowering, but also lead them down paths that confirm their biases, especially if they distrust institutions like NASA or governments.
Yeah, do your own research often translates to find videos that tell you what you want to hear, rather than critically evaluating sources or scientific methodology. It's a tricky line to walk, honestly.
Precisely. And for many, the flat Earth model offers a perceived simpler explanation. They suggest the Earth is a disk with the North Pole at its center and Antarctica forming an ice wall around the perimeter. The Sun and Moon are then small, local objects orbiting above the disk.
Okay, so let's unpack that for a second. If the Sun and Moon are local, small objects, how do they explain day and night and seasons? That seems like it would create a whole new set of astronomical headaches.
They propose that the Sun acts like a spotlight, shining down on different sections of the disk as it circles above. So when it's over North America, that area has day, while the other side of the disk is in night. But this model struggles to explain global time zones, the consistent path of stars in both hemispheres, and eclipses, for example.
Right, because if the sun's a spotlight, everyone on the disk under the light would experience noon at the same time, which we know isn't true. And the concept of circumnavigation, like Magellan's voyage, where you just keep sailing in one direction and end up where you started, how do they explain that on a disk?
That's a big one. On a flat Earth, if you sail west, you'd eventually hit the ice wall of Antarctica. They would argue that all circumnavigation is actually just traveling in circles on the disk, eventually bringing you back to your origin, without ever proving the Earth is a sphere. But it requires some significant mental gymnastics to fit all the observations.
And what about gravity? The whole concept of things falling down uniformly across a disk versus towards the center of a mass like a sphere, that's a huge hurdle, isn't it?
Indeed, flat Earth models typically reject conventional gravity. Some suggest the disk is constantly accelerating upwards, pushing us down. Others propose a density-based gravity, where objects fall because they're denser than the air around them, but this doesn't hold up under scrutiny for things like orbital mechanics or tides.
It sounds like every answer to one problem creates 10 new ones, which is often how these things go, I guess. So, beyond the ancient Greeks, what are some of the more modern, undeniable pieces of evidence that point to a spherical or oblate spheroid Earth?
Well, satellite imagery is perhaps the most direct. We have countless photos and videos from space, from agencies all over the world, showing a spherical Earth. Beyond that, there's the Coriolis effect, which explains why hurricanes spin differently in the northern and southern hemispheres, an effect only possible on a rotating sphere.
Ah, the Coriolis effect. I remember learning about that. It's a great example because it's an observable phenomenon that directly supports a rotating globe. You can't just hand-wave that away with a spotlight sun, can you?
Exactly. Then there's the fact that different constellations are visible from different parts of the world. You can't see the Southern Cross from Europe, and you can't see Polaris, the North Star, from Australia. That's only possible if you're on a curved surface.
That's a very intuitive one. You literally look up at the sky, and depending on where you are on the planet, you see different things. It would be the same sky everywhere on a flat plane.
Right. And lunar eclipses, when the Earth passes between the Sun and the Moon, its shadow on the Moon is always circular. Only a sphere can cast a consistently circular shadow from any angle. A disk, depending on its orientation, would cast an elliptical or linear shadow.
That's another classic, powerful argument. You just look up, see the curve, and it's there. So when people say they don't see the curvature from an airplane, how do we address that?
That's down to scale and human perception. The Earth is enormous. Even at cruising altitude, say 35,000 feet, you're only seeing a tiny fraction of that huge curve. You'd need to be much, much higher, like a stratospheric balloon or in orbit, to clearly discern the curvature with your naked eye without distortion from window shapes or lenses.
So it's not that the curve isn't there, it's just so gradual over the distance we can perceive from typical human vantage points that it appears flat. It's like standing next to an elephant, you can't see its whole shape from an inch away.
Exactly. The Earth's curvature is roughly 8 inches per mile squared. That means over a mile it drops 8 inches, over 3 miles it drops about 6 feet. That's a tiny drop over distances we're used to observing. It just isn't noticeable unless you have vast, uninterrupted views or sensitive instruments.
And that's the key, isn't it? The difference between anecdotal observation and systematic, scientific measurement. Science builds models that explain all the observations, not just the convenient ones.
Absolutely. Science isn't about proving one idea right and then stopping. It's about constant testing, refinement, and using evidence to build the most robust and predictive models. The oblate spheroid model explains everything from gravity to satellite orbits to time zones, and it's backed by centuries of cumulative data.
It also explains why some people might suggest other forms for the Earth, like a hollow Earth. Though that's probably a whole other podcast episode, isn't it?
Oh, definitely. The hollow Earth theory is another fascinating historical idea, often involving entrances at the poles and an inner sun. It dates back to the 17th century but doesn't align with modern geology or seismology, which clearly show a dense core beneath us. But again, it speaks to humanity's endless curiosity about what lies beneath our feet.
It's all about that sense of wonder, isn't it? The desire to uncover a deeper truth, even if it contradicts what's commonly accepted. It's part of what makes us human.
It is. And while it's important to question and to think critically, it's equally important to understand the scientific method and how evidence is gathered and validated. Because while doing your own research is great, relying on established scientific consensus, which has been rigorously tested, is usually a more reliable path to understanding.
So, to wrap this up, the real form of the Earth, based on overwhelming scientific evidence, observation, and centuries of human inquiry, is an oblate spheroid. A slightly flattened, rotating sphere, not a perfect ball, but definitely not flat.
Precisely, and it's a beautiful, dynamic form at that. It's what gives us our seasons, our varied climates, and allows for the incredible journey of life we see around us. It's humbling to think about.
Absolutely. It's been a truly spherical journey today on Cosmic Queries. Thank you, Jane, for shedding light on such a fundamental yet often debated topic.
My pleasure, Don. Always a pleasure to explore the cosmos, even when it's just beneath our feet.
And thank you to all our listeners for tuning in. Keep asking those big questions, keep looking up, and keep exploring the incredible universe around and beneath you. We'll catch you next time.